These worked example videos are associated with Module 1. They may look similar to examples that were in the lecture videos and are just meant as an additional resource if you would like to see these problems gone through step by step. Our first problem is a sample exercise about unit conversions. The problem is the masses of diamonds are usually expressed in carats, and 1 gram is equal to exactly 5 carats. The Star of Africa is one of the world's largest diamonds, having a mass of 530.2 carats. What is its mass in grams? We will look at this through the COAST framework so that you have a better idea of how you can use that framework to go through some of the more challenging problems when we get to them. So the things that we have are a mass value in carats, and we want to convert it to grams. The problem also tells us there are 5 carats in 1 gram. We can use the equivalencies to write a conversion factor. And we saw conversion factors in the lecture videos, and so you know that you could write it as a fraction with either value on the top because they equal each other exactly. So this is like writing 1 because they mean the same thing. The way that the conversion factor here is written is that 1 gram is equal to 5 carats by having 1 gram over 5 carats. Now, this is set up knowing where the problem is going to go, but there'd be nothing wrong with writing both versions and then seeing which version you need when it's time to solve the problem. So when we use this conversion factor, the value we have is in carats, and we're trying to convert it to grams. So we need something that will cancel out carats. So it needs to have carats in the bottom, and then will give us an answer in grams. So grams is in the top. So our answer for this is 106 grams is the mass of this diamond. So the last part of COAST is to think about it. So, let's see if this answer makes sense. The calculated mass might seem really large for a diamond. So 1 gram is about the mass of an M&M. One piece of M&M candy. That's how it's sometimes described. So 100 M&M candies, that's a pretty big diamond. But this is also an enormous diamond. So if you're looking for something to compare it to, engagement rings are probably the most common way that you will see diamonds referred to with their carat value. And 1 carat is about how much we have in an engagement ring. So how many grams would that be? Take a minute to think about that one. So this is a very extremely large diamond and is worth about $1 billion. So just a summary of this problem, everything that we went through. So the collect and organize stage, we had a mass value in carats and we wanted to convert it to grams. We were also given enough information to set up the conversion factor, which is what we did in the analyze portion. In the solve portion, we put that conversion factor with our starting value and got an answer value in grams. And then to think about it, yeah, this is pretty big, but it's also a very large diamond if it has that many carats. This worked problem will look at using significant figures in calculations. The volume of a nugget of shiny yellow mineral with a mass of 30.01 grams is determined by the method of water displacement. The way that this is done is that we have a 100 ml graduated cylinder that contains 56.3 mils of water before the nugget is added and 62.6 mils after it is added. What we want to find is the nugget made of gold? And we're given the density of gold, which is 19.3 grams per mil. So collect and organize. We have the mass of the nugget, and we have enough information from the water displacement to find its volume, and density is the mass divided by the volume. The volume of the nugget is the difference between 62.6 mils and 56.3 mils, or about 6 mils. So that's just an approximation. The ratio of the mass, 30.01 grams to volume, about 6 mils, is about 5 grams per mil. So we can estimate before going into this problem what the density of the shiny yellow mineral is and determine whether or not it's gold before moving on and doing the exact calculation. So we know that we should get an answer that's about 5 and that it is not gold. So density is mass divided by volume. So the exact mass is 30.01 and the exact volume is 62.6 minus 56.3, which is 6.3. And if you divide these out exactly, it's 4.7635 grams per mil. So definitely not gold, and we got an answer that's pretty close to 5. Next, we have to apply significant figures. So the significant figures that we have are from the mass and from the volume. The mass value has 4 significant figures, and this is just how the number is given to us, 30.01. The volume has to be determined from how the calculation is done. So in addition and subtraction, you look at the place. So we usually say the least number of decimal places, but it applies for any placeholder. So the decimal place that we're going to is the first decimal place, which means that 6.3 in terms of volume has 2 significant figures. If you take a number with 4 sig figs, divide it by something with 2 sig figs. When we do multiplication and division, we use the least number of sig figs. So our answer will have 2 sig figs, which means that we would report it as 4.8 grams per mil. So think about it. Our rough estimate helped us determine that this was not gold before we went on to do the exact calculation. And then just a summary slide here. So we had the mass and we had water displacement data that let us calculate volume. Then we could calculate density because density is mass divided by volume. We used an estimate to figure out before going in that this was not going to be gold and that when we got an answer, it should be close to 5. Our actual answer did come out close to 5. And then we applied significant figure propagation rules to determine that our final answer should have 2 sig figs.